and how galaxies are born. Let's make a telescope to help us. So we spec the next generation space telescope after Hubble to be exquisitely tuned to show us galaxies beyond.
These are the images captured by Hubble telescope, and these are the images captured by James Webb telescope. Now, if you look at the James Webb footage compared to that of Hubble, you'll realize the image is much clearer than that of Hubble. But what if I tell that isn't all about it? Well, here is the catch. What Hubble couldn't see, JWST is giving us a new insight about what they look like, challenging all notions of what we knew about the universe. I'm talking about nothing else but the blurred galaxies we observe on James Webb footage. What are the meaning of this new discovery? How does it explain the origin of the universe? Join us as we are about to unveil the mysteries of the cosmos. The James Webb Space Telescope, JWST, is a remarkable space observatory that has been designed to explore the mysteries of the universe. It is often called the successor to the Hubble Space Telescope because it will take space exploration to a whole new level. Now, you might wonder how much such an incredible piece of technology costs. Well, the JWST has been a significant investment with an estimated cost of around $10 billion. That may sound like a staggering amount, but when you consider the complexity of building and launching a space telescope, it starts to make sense. The purpose of the JWST is to observe the universe in ways that were not possible before. It is equipped with state-of-the-art instruments that can detect many different types of light, including infrared light. Infrared light is important because it can reveal objects and phenomena that are otherwise hidden from our view. One of the main goals of the JWST is to study the formation and evolution of galaxies. By observing galaxies in the early universe, scientists hope to gain insights into how galaxies were born and grew over billions of years. This knowledge can help us better understand the origins of our own galaxy, the Milky Way. The JWST will also focus on studying exoplanets, which are planets orbiting stars outside our solar system. Scientists are eager to find planets that could potentially harbor life or have environments similar to Earth. By analyzing the atmospheres of exoplanets, the JWST can provide valuable clues about their composition and the possibility of habitability. Additionally, the JWST will investigate the formation of stars and planetary systems. It will peer through the dusty regions of space where stars are born, helping scientists understand the processes that lead to the creation of new stars and planets. This knowledge can shed light on the conditions necessary for life to emerge. In order to accomplish these goals, the JWST has been built to be highly sensitive and precise. It is designed to operate in the coldness of space, far away from the heat and interference of Earth's atmosphere. By being situated in space, it can capture clearer and more detailed images, allowing scientists to unlock the secrets of the universe. You see, the JWST wasn't just created to pop up amazing images of the universe, rather to continue where Hubble ended. But it turns out that JWST outperformed what was expected out of it, bringing out images that takes us back into the very early universe, even earlier than the theoretical Big Bang itself. This gives us a glimpse of what the universe was like before the theoretical Big Bang era, leading to the crisis we face today in astronomy and cosmology. Several debates about the origin of the universe has always sparked the entire domain of astrophysics and cosmology. However, the latest findings of JWST can finally help us solve this problem. Unlike us, who love gazing at the night sky and often wonder about the vastness and magnificence of the cosmos, what does astronomists and cosmologists study out there with such massive telescopes? Astronomy is the fascinating study of everything that exists beyond our planet Earth. It is a science that explores the vastness of space, including stars, planets, galaxies, and other celestial objects. Astronomers use powerful telescopes and advanced technology to observe and understand the universe. Imagine looking up at the night sky and seeing countless twinkling stars. Well, astronomy goes beyond just admiring their beauty. It seeks to answer questions like, what are stars made of? How do they form and die? Are there other planets like Earth out there? How did the universe begin? And how will it evolve in the future? One of the primary focuses of astronomy is stars. Stars are giant balls of hot gas that shine brightly in the sky. By studying stars, astronomers can learn about their composition, size, temperature, and life cycle. They can also determine how far away stars are and how they move through space. This knowledge helps us understand the vastness and complexity of the universe. Another exciting aspect of astronomy is the study of planets. Our own solar system, which consists of the sun, planets, moons, and other objects, is just a tiny part of the universe. Astronomers investigate planets within our solar system, like Mars and Jupiter, as well as planets orbiting other stars known as exoplanets. They seek to understand their atmospheres, surfaces, and potential for supporting life. Galaxies are enormous collections of stars, gas, and dust held together by gravity. They come in various shapes and sizes. The Milky Way, our home galaxy, is just one among billions in the universe. Astronomers study galaxies to learn about their formation, structure, and evolution. They examine how galaxies interact with each other and understand the supermassive black holes that exist at their centers. Astronomy also delves into the mysteries of the early universe. By studying the oldest light in the universe, known as cosmic microwave background radiation, scientists can learn about the origins and development of the cosmos. They investigate the Big Bang theory, which suggests that the universe began with a massive explosion, and they try to understand how galaxies and other structures formed over billions of years. To observe these celestial wonders, astronomers use a variety of tools and instruments. Telescopes are the most important of these. They gather and focus light, allowing scientists to see distant and faint objects. Some telescopes are located on Earth, while others are placed in space to avoid the interference of Earth's atmosphere. In recent years, technological advances have revolutionized astronomy. Powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, provide stunning images and collect valuable data that help scientists unravel the mysteries of the universe. On the other hand, cosmology is a branch of science that focuses on understanding the origin, structure, and evolution of the entire universe as a whole. It goes beyond the study of individual celestial objects, like stars and galaxies, and seeks to unravel the larger picture of how the universe came to be and how it operates on the grandest scales. While astronomy examines the specific properties and behaviors of celestial objects, cosmology takes a step back to investigate the universe as a unified entity. It addresses profound questions about the nature of space, time, and the fundamental laws of physics that govern the cosmos. One of the central pursuits of cosmology is to understand the origin of the universe itself. Scientists propose various theories and models to explain how the universe began and how it has evolved over billions of years. The prevailing theory, known as the Big Bang theory, suggests that the universe emerged from an incredibly dense and hot state around 13.8 billion years ago. Cosmologists study the aftermath of the Big Bang, the expansion of space, and the formation of galaxies and other large-scale structures. Cosmologists also investigate the composition of the universe. Ordinary matter, the stuff that makes up stars, planets, and everything we can see, accounts for only a small fraction of the total matter and energy in the universe. The rest is made up of mysterious entities called dark matter and dark energy. Dark matter does not interact with light and remains invisible, but its gravitational effects are observed on cosmic scales. Dark energy, on the other hand, is thought to be responsible for the accelerating expansion of the universe. Cosmologists strive to understand the properties and roles of dark matter and dark energy, as they play a crucial role in shaping the universe's structure and destiny. In addition to the origin and composition of the universe, cosmology explores the large-scale structure and evolution of cosmic objects. Scientists study how galaxies form and cluster together, how they merge and interact, and how these processes shape the distribution of matter in the universe. They also investigate cosmic microwave background radiation, which is the afterglow of the early universe, to gather clues about the initial conditions and early stages of cosmic evolution. To tackle these complex questions, cosmologists employ a range of scientific tools and methods. They use powerful telescopes and observatories to observe distant galaxies and measure the properties of cosmic radiation. They also make use of advanced mathematical models and computer simulations to simulate the behavior of the universe under different conditions. Cosmology is an ever-evolving field, and new discoveries continue to reshape our understanding of the universe. From the confirmation of the Big Bang theory to the detection of gravitational waves, cosmologists contribute to our knowledge of the universe's past, present, and future. The James Webb Space Telescope, JWST, is revolutionizing our understanding of the universe with unprecedented observations of distant galaxies and young star systems. As astronomers analyze more data from the most powerful space telescope ever launched, new theories are beginning to emerge that could reshape core models of cosmology. One surprising early finding is the discovery of massive galaxies forming much earlier than expected, within the first billion years of the Big Bang. This poses challenges to theories of galaxy evolution that predicted it would take longer for the first large clusters to coalesce. It indicates that initial seeds for galaxy formation may have begun growing even earlier in the universe's history. Another potential new theory relates to observations of dust clouds in very young star systems. The amount and distribution of dust and gas surrounding infant stars is providing clues about planetary formation processes in a way not possible before. Astronomers are exploring whether standard models of how planets like Earth coalesced need to be modified based on the new insights. Perhaps most intriguing are Webb's views into the very earliest epoch of cosmic history called the Cosmic Dawn, when the first luminous objects were emerging after the dark ages of the universe. Spectacular spectra are revealing the composition of gases surrounding the earliest galaxies and quasars. This promises to refine our understanding of reionization, when light from newborn stars and black holes transformed the universe from neutral to ionized. As more data pours in from the observatory's sweeping surveys of galaxies both near and far, astronomers expect fundamentally new questions and theories will arise. JWST may uncover phenomena and processes not anticipated based on past models. With its ability to study astronomical objects both farther back in time and in finer detail than ever before, this powerful telescope is sure to continue sharpening our view of the universe's origins and evolution in unexpected ways. In one of its deepest exposures yet, the James Webb Space Telescope has captured over 15 distinct galaxies that are estimated to be over 13.5 billion years old, providing new insights into the early universe. The discovery marks the largest number of galaxies from the first 500 million years of the universe ever observed at one time. The galaxies appear as faint red or orange blobs in Webb's image, taken as part of its Cosmic Evolution Early Release Science Survey. Their great distance means the light observed left them just 300 million years after the Big Bang. This presents astronomers with an unprecedented opportunity to study galaxy formation in the earliest epochs. Analysis of the galaxy's spectra could reveal clues about their composition, masses, ages, and initial stages of star formation. Some may represent the very first generation of stars, which emerged from the otherwise dark universe as it became lit with early light. The data may also provide insights into how small proto-galaxies merged together in the initial phases of the universe's structure formation. Perhaps most intriguing is that a few of the galaxies appear to be interacting or in close proximity to one another already at this early time. This was unexpected, as it was believed the first galaxies would still be quite isolated in the initial 100 million years. Their proximity raises questions about how galaxy seeds came together and evolved more rapidly than theories predicted. As Webb conducts deeper exposures to detect even more distant galaxies, astronomers will gain new perspectives on cosmic evolution near the so-called epoch of reionization, when the universe transitioned from neutral to ionized. Additional study of these 15 early galaxies is sure to yield fresh insights to sharpen models of galaxy assembly in the young universe. JWST has begun opening new windows into the very first light of the cosmos. Another surprising discovery made by the James Webb Telescope is observing a huge amount of galaxies vanishing in thin space. The Great Unconformity represents one of the most significant gaps within the geological record of our planet. Spanning between 100 million to 1 billion years, it is essentially a long period of missing time, where there is very little evidence of geological processes occurring on Earth. This enormous gap in the rock and fossil record indicates that whatever conditions existed during this time, they did not permit the formation and preservation of new sedimentary layers. The rocks that were being formed were almost entirely eroded away, leaving almost no clues as to what the Earth was like. It's thought that during the Great Unconformity, the planet underwent either an extended period of extreme weathering and erosion, or a massive global tectonic event such as a period of mountain building. Either scenario would have destroyed and removed much of the existing rock formations from before this time. When normal geological activity resumed after the Great Unconformity, the Earth looked dramatically different. Younger sedimentary layers were deposited directly on top of much older crystalline basement rocks from pre-existing formations. The contact between these two groups of rocks is known as an unconformity, with evidence the older layers underwent geological weathering and erosion during the gap in between. By disrupting the long-term continuity of the geological record, the Great Unconformity represented a major revolution in the evolution of Earth that set the stage for new phases of mountain building, changing sea levels, and development of new land masses. It ultimately altered global climate and environmental conditions for hundreds of millions of years. While many questions still remain about what transpired during this mysterious period, it was an interval of immense change that modified the face of the planet. The Great Unconformity serves as a reminder of Earth's dynamic nature and how disruptive geological events can profoundly influence its long-term development. Just in the same way as the Great Unconformity is the mystery of the disappearing galaxies in space. With the patterns and behavior of this phenomenon, scientists called it the Great Void. The Great Void is an enormous empty region of space located within the Eridanus supervoid, a vast area spanning nearly 1 billion light-years. At its center lies an almost completely empty zone known as the Great Void, measuring around 300 million light-years across. This makes it one of the largest voids discovered in the universe. While not entirely empty, the Great Void is incredibly sparse compared to other areas of the cosmos. Within its borders, there exist very few galaxies, stars, or even dark matter. This is highly unusual, as galaxy clusters and groups are normally densely packed across the universe. The complete absence of structures across such a massive scale within the Great Void came as a major surprise to astronomers. Upon its discovery, scientists were left perplexed as to what could have caused such an enormous empty region to form. Several hypotheses have been proposed over the years to try and explain this puzzling phenomenon. One theory suggests a primordial black hole could be responsible. Early in the universe's formation, small quantum black holes may have developed, capable of consuming all surrounding matter and leaving behind an immense void. Alternatively, some propose the effects of hypothetical cosmic strings could be to blame. These ultra-dense hypothetical objects hypotheses to have formed during the early universe are thought to have interacted in strange ways with matter and gravity, potentially pushing particles away and carving out vast empty spaces. The third possibility is that the Great Void may simply be a result of the natural variations expected to occur across the inhomogeneous universe on the largest of scales. However, the most intriguing part is that it seems not only galaxies are absent from the Great Void, but they have disappeared altogether. Through studying the cosmic microwave background and patterns of distant galaxy distributions, Astronomers have found evidence that suggests entire galaxy clusters once existed within the boundaries of the Great Void, but have since vanished without a trace. Their disappearance into the emptiness of the Great Void remains one of the greatest mysteries in modern astrophysics. Continued studies of this remarkable feature of empty space aim to better understand what could cause galaxies to disappear so completely. Could the sudden disappearance of these galaxies be a transition of galaxies into another universe? Or how will the Big Bang explain the sudden vanishing of 100 billion of galaxies just like that? This tells us that our universe is more deeper than we know. For decades, the standard cosmological model placed the Big Bang around 13.8 billion years ago. However, some of the very early galaxies spotted by JWST seem too advanced based on their size and complexity to have formed in the short time since that supposed moment of creation. The telescopic images show massive clusters of stars and intricate galactic structures existing much earlier than models predicted was possible. According to our current understanding of galaxy formation and growth, it takes billions of years for these kinds of large, evolved galaxies to develop under normal astrophysical processes, like the gravitational attraction of dark matter halos and collisions between smaller galactic progenitors. But the galaxies JWST observed appear to have already exhibited such complexity and maturity within the first billion or so years after the proposed Big Bang, leaving too little time for conventional development. This implies galaxies either assembled much faster than expected, or that our calculation of the universe's age is inaccurate. If galaxies started forming long before 13.8 billion years ago, it challenges the very foundation of the Big Bang theory, which states all cosmic history flows from a single explosive event at this point in time. It suggests the reality may be more complex, with galaxies arising earlier than the standard model can account for. Astronomers are now reconsidering alternative theories like Fritz Zwicky's proposal from the 1920s that redshift is caused by light gradually losing energy over long voyages, not from expansion. Combining this tired light idea with theories of changing physical constants produces a universe estimated to be twice as old. In either case, the Webb telescope's revelations have thrown into question our timeline for the emergence of the first objects in the cosmos. Further research is needed, but it seems current models may require substantial revision to align with the new empirical data. One of the key ways scientists have calculated the vast distances to galaxies and determined the expansion rate of the universe is by measuring a phenomenon called redshift. Redshift is where light from distant objects appears reddened and is generally attributed to the Doppler effect of objects moving away from us as space expands. The greater the redshift, the faster the galaxy is receding and the farther away it is assumed to be. Astronomers use redshift measurements to infer how quickly the universe stretches with time. This data has supported the Big Bang model, placing the birth of the cosmos at 13.8 billion years ago. However, the unusually ancient galaxies seen by JWST have prompted researchers to re-examine our understanding of redshift. If these galaxies predate the supposed Big Bang, it implies redshift may be caused by something other than expansion alone. An alternative theory first proposed in the 1920s suggested redshift could partly result from photons gradually losing energy during their long journey through space, which was dubbed tired light. This idea was dismissed, but is now being revisited in light of the new telescopic findings. Examining redshift through the lens of tired light, combined with theories of changing physical laws over cosmic history, produces older estimates for the universe's age that better align with the advanced galaxies. This calls into question whether redshift truly traces the stretching of space, or if additional factors cloud our interpretation. If the redshift distance relationship is more complex, it weakens the case for an expanding cosmos launched by the Big Bang. Clearly, more investigation is needed, but JWST has highlighted potential flaws in how astronomers have been using redshift alone to map the structure and evolution of the universe across billions of years. New models may be required, The surprising discoveries made by the James Webb Space Telescope have led some scientists to re-examine older cosmological theories that were previously dismissed. One such idea gaining new attention is Fritz Zwicky's tired light hypothesis from the 1920s. Zwicky originally proposed that the redshift observed in distant galaxies, normally attributed to the Doppler effect of expansion, could instead be caused by photons gradually losing energy as they travel through space for billions of years. Over such immense distances and timescales, interactions with intergalactic gas dust may slowly deplete the light particle's energy reserves. Zwicky called this the tired light theory. It challenged the standard interpretation that redshift traces the stretching of space itself. However, without compelling empirical evidence, the tired light hypothesis was abandoned in favor of the emerging Big Bang model, placing the universe's age at around 13 to 14 billion years old. But the exceptionally ancient galaxies detected by JWST, appearing too evolved to fit within this time frame, have caused scientists to re-examine tired light and other non-standard ideas. Canadian researcher Rendra Gupta combined Zwicky's theory with concepts of evolving physical constants, calculating a universe age of over 26 billion years through this modified framework. Remarkably, this older estimate aligns better with observations of the early universe's advanced galactic structures. It demonstrates that tired light, coupled with time-varying cosmic parameters, cannot be so easily discarded and may offer a more cogent explanation than the simple expanding universe narrative. While far more research is still warranted, the potential of tired light to resolve conflicts between theory and evidence suggests some past alternatives to the standard cosmology were prematurely ruled out. JWST's images appear to have opened the door to a re-evaluation of light's role in shaping our view of the universe's origins. If the cosmological model needs major revision based on these new observations, it has profound implications for our understanding of time and space itself. Without a defined starting point in the form of the Big Bang, it means the universe may have no clear beginning or definitive age. It could extend infinitely far into the past, with matter and galaxies existing continuously for all time rather than emerging abruptly from an explosive genesis. Alternatively, some theorists speculate we may be observing only one smaller region within an infinitely larger or even multiverse of domains. On these scales, our observable cosmos might represent just one tiny fragment of a hyperuniverse, lacking any absolute boundary or birth date. If the redshift distance relationship cannot be solely explained by expansion, it removes the assumption that the universe has been consistently inflating since some initial point in the distant past. The very fabric of space-time may not be uniformly expanding or have a knowable geometry stretching back unbroken to a single origin. Without a standard Big Bang timeline and reliable measure of distances, astronomers can set no firm limits on the universe's potential size and age. It opens up possibilities that make our current conceptualization of the cosmos as a whole seem limited. Conceivably, there may be structures or processes outside our observable patch and not explainable by existing theories. Major adjustments would be required to physics, cosmology, and philosophy. But perhaps the greatest lesson is our understanding of the grand scheme is incomplete and new paradigms will be needed to integrate what telescopes like JWST are revealing about the marvelously diverse realities beyond our planet. The surprising findings from the James Webb Space Telescope have sent major shockwaves through the scientific community. Discovering galaxies that appear far older than current models suggest has thrown the entire field of cosmology into a state of upheaval. For decades, astronomers have worked within the framework of the standard cosmological model, which places the Big Bang around 13.8 billion years ago. All of our theories about the formation and evolution of galaxies, stars, and planetary systems have been built upon this foundation. But the highly evolved galaxies spotted by JWST in the very early universe contradict the timelines established by our prevailing cosmological paradigm. Their advanced structures seem to require many more billions of years to develop than current theories allow. This means the core mathematical models and equations used to describe the universe's expansion, composition, and aging may need reworking from the ground up. Concepts like dark matter and dark energy that were introduced to patch problems may no longer suffice. Leading thinkers are now divided, with some defending the standard framework and others arguing an outright revolution is warranted. Younger researchers are more open to new perspectives, while senior figures aim to preserve the existing architecture. With the field's entire conceptual infrastructure facing invalidation, cosmologists have been thrown into disarray. No new consensus has yet emerged on how to reconcile these discordant data points with over a century of accumulated knowledge. Major conferences are abuzz with spirited debate as scholars scramble to find solutions. Regardless of the resolution, it is clear that one of the greatest scientific paradigm shifts may be underway. JWST has succeeded in toppling comfortable assumptions and forcing a radical reevaluation of humanity's place in the grand scheme. In short, these unexpected findings have sparked an unprecedented crisis, with many long-held beliefs now at stake in a dramatic showdown between theories and observations. At the moment, the only option which can be used to handle such a crisis can be done by using a Canadian astrophysicist, Rendra Gupta, proposal, a novel cosmological theory that seeks to address some of the inconsistencies between the standard models and recent observations from the James Webb Space Telescope. His theory combines two theoretical concepts, Fritz Zwicky's tired light hypothesis from the 1920s and the possibility that fundamental physical constants may vary over cosmological timescales. Zwicky originally suggested that the redshift observed in distant galaxies, which is usually attributed to the Doppler effect from cosmic expansion, could instead be caused by photons gradually losing energy as they propagate through intergalactic space for billions of years. He called this the tired light hypothesis. While considered speculative for many decades, Gupta believes reviving and incorporating Zwicky's tired light idea into cosmological calculations, along with allowing constants to evolve, could provide valuable insight. The theory goes that interactions between photons and intergalactic gas-dark matter over immense journeys across the universe would slowly deplete their energy reserves in line with Zwicky's hypothesis. Meanwhile, constants like the speed of light that govern physical behavior could have been different in the early universe versus today. By developing new mathematical models combining tired light with time-varying constants, Gupta claims to have resolved certain inconsistencies. When applying these modified models to analyze cosmological observations like the redshift of distant galaxies, an age is produced for the universe that is at least 26.7 billion years. This older timeline would allow for the evolved galaxies discovered by JWST to have formed through conventional processes without needing to revise existing frameworks of galaxy evolution. While experimental tests are still ongoing, Gupta's theory demonstrates that reconsidering previously dismissed entities like tired light, coupled with non-static constants, presents a novel way to reconcile observations with theory. It remains an area of active discussion and research. The theoretical work of Canadian astrophysicist Rendra Gupta has offered a fascinating new lens for interpreting the surprising data from the James Webb Space Telescope. By combining Fritz Zwicky's tired light concept with theories of evolving fundamental constants, Gupta has opened the door to a more dynamic view of the cosmos. For over a century, physicists have generally assumed the basic laws and parameters that govern the universe are invariant. That is, they remain perfectly fixed over space and time. The speed of light, for example, has always been treated as a constant 299,792,458 meters per second. But Gupta's models entertain the possibility that constants may subtly change as the cosmos expands and evolves. Allowing for variables like a smaller speed of light value in the early universe has significant implications for deducing distances, timelines, and physical processes across eons. If constants varied, it could help explain anomalies like the unexpectedly advanced galaxies seen by JWST that seem to defy the age predicted by standard cosmology. Their existence makes more sense under a paradigm of gradual constant fluctuation over cosmic history. By considering a universe whose rules change over its lifetime rather than remaining rigidly static, new theoretical avenues open up. It presents a more dynamic, complex cosmos than the oversimplified clockwork universe envisioned before. While still speculative, Gupta's innovative approach highlights our limited perspective and shows there may be greater richness to discovery as observational techniques like JWST push our horizons. It reveals how willingness to reassess assumptions can provide a route to new insights that resolve old paradoxes. Overall, Gupta's work exemplifies how questioning even fundamental premises can catalyze advances in scientific understanding of the grander universe that continues surprising us at every turn. While all the newly proposed theories does not seem too convincing, what do you think about the origin of the universe from James Webb's observation? Do you think our universe has no start and no end? Or you think we are living in one of many universes? Let me know your thoughts in the comment section below. As for me, I remain certain that there are still a lot lurking out there than our eyes can see, giving us an understanding from JWST's discovery that there might be even more than we can perceive, yet unseen by any man-made telescope. This implies that to know more about our cosmos, we'll have to develop new models from time to time till the dusk of humanity's existence. So, that is it for today's video. If you enjoyed it, please subscribe to our channel for more videos about our cosmos. See you in the next video.